Our lesson for today will be on analysis of structures. Analysis of structures. And under this procedure, or under this topic or analysis of structures, we have two methods. We have by method of joints, and secondly by method of sections. But we will first discuss this method of joints. So we need to have a sample problem for this, for you to be able to understand it clearly. So sample problem that we need to draw. Okay, so it is supported by a hinge or a pin at this joint. We also have a support at the other end of the truss with a roller. Okay, this is a roller, and this is a roller, and this is a hinge. And of course, this truss is loaded by these loadings, or we have these loadings. We have 100 kilonewton, a magnitude of a load of 100 kilonewton. Then at this joint we have also a force that is acting that direction, and of course this is 25 degrees from the horizontal, and this load or loading has a magnitude of 120 kilonewtons. Okay, so the dimension of the, we need to also know, or let's try to reflect the dimensions of the truss, wherein this is the height is 3 meters, and we have also this, actually this is not to scale. Okay, so this is 5 meters, and we have also 5 meters in there. For you to be able to, of course, solve or to analyze this particular truss by method of joints, let's try to indicate what is this joint, this joint, this joint, and that joint. Okay, so we'll try to represent them with alphabets. So this is joint A, joint B, joint C, and joint D. Is that clear? So with this, we will now be able, of course, to analyze it now. Okay, so as we have been doing, let's indicate the given. Okay, so the given will be the figure and data shown, and in here, what are the requirements will be, or the required items for this problem is of course, you are going to determine the forces or stresses in each member. Okay, in each member. So what are those members? let's try to identify them. So we have member, okay, this is member AB. Okay, member AB, this one AB. Then we have member AC, this AC. Okay, AC. And we have member BC, this one. Okay, BC. The next is we have BD, member BD, okay, of the trust. So BD, and last but not the least we have CD. Okay, if you will notice it, this member is called member AB, this is AC, this is BC, this is BD, and that is CD. Okay, so those members made up or composed actually the trust. Okay, so next is we need to, of course, write also the solution. So this is how you are going to, of course, the process that we are usually doing it ever since. You need to state the given. You need, of course, to state or to determine or to identify the requirements, and of course the solution. Okay, but before you are going to start the solution, actually this is already part and parcel of the solution, the illustration, etc. Okay, so in doing again class, or let's try to continue this. Okay, so considering again this trust, since this is a hinge, so I have told you earlier that there should be, of course, the vertical and the horizontal reactions, or the components of the reaction that is acting on this. Okay, so we need to, since this is joint A, so let's try to designate this as reaction, the horizontal or the vertical reaction at A. So we represented the RAB, the reaction at A, vertically acting. Okay, and this one is the reaction at A, horizontally acting. So let's try to have the imaginative, or the representation of the reaction, actually reaction at A, which will be acting on this point. This is actually RA. Okay, because why is this so that it is diagonally directed, or it's going, or the direction is diagonal? Because there is also a diagonal force in there that is being exerted on the truss. So normally there will be a reaction that is diagonally counteracting this particular loading. Okay, for again, please remember, when you are going to put, of course, to analyze a joint with a hinge as a support, so we have the horizontal component of this particular reaction at A, and the vertical component of this particular reaction A. Actually, this is not in analyzing trusses maybe by method of joint or by section, but we are talking about joints. Unless otherwise a requirement, you are going to solve this, then you indicate it. But if it is not, in analyzing again joints, we just simply need horizontal forces and vertical forces along the x and along the y. Okay, so in here at joint D, since this is a roller, as we have discussed before, we have the reaction in here as a vertical reaction only, because a roller will be just counteracting, or a roller support will just be reacting vertically. So we just simply have this as RD, kasi wala namang RDH or RDV, so let's just have it RD. So but for you to be able to solve this, you must again to recall the three important equilibrium equations in statics. Okay, so we have let's try to state. So what are those? So equilibrium equations. What are these? So number one, we have summation forces horizontal is equal to 0 positive going to the right. Number two, summation forces vertical is equal to 0 positive going up. And we have the third equation, equilibrium equation, summation moments at a certain point is equal to 0 positive clockwise moments. So we can also designate this, or we can also call this one, if ever you are going to use your x and the y. So we have summation forces x is equal to 0 positive to the right. We have also summation forces y for the vertical component is equal to 0. Okay, 0 positive going up, and this will remain. Okay, so summation moments at certain point will still be equal to 0 positive clockwise moments. Okay, so for our solution, for the continuation of our solution, let's now try to have the first equilibrium equation to be used for us to be able, of course, to solve for RAV, RAH, or if ever required, RA, and of course RD. So if you're going to take summation moments at this point A, so you need to write summation moments at A is equal to 0 positive clockwise moments. Okay, so if you're going to investigate your truss, if you're going to take summation moments in here, so what are the forces that are acting clockwise? What are the moments? What are the moments? So the moment of this force will be clockwise. Okay, how about this? So the since as I've said earlier, that what is necessary in, of course, analyzing trusses is that you need to have the vertical and the horizontal components of any force acting diagonally. So you need to plot for you to have a guide. You need to draw if ever you want to draw for you to have a guide. So we have what is this vertical component of this force? It will be 120 kilonewtons sine of 25 degrees. Okay, then what will be the horizontal component of this diagonal force? it will be 120 cosine 25 degrees. So going back again to our equation, summation moments at A, so you need to consider, so all this component is acting counterclockwise, this component is clockwise, and this component acting clockwise. So with this, so what is the force, or yes, what is that particular force that is acting counterclockwise? This is just a single force that is acting counterclockwise, as you notice from here to that. So what is the effect? It will be counterclockwise. So as you have seen in here, summation moments at A is equal to 0, positive all clockwise moments. So let's try to write. So first is we have 100 times the moment arm. What's the moment arm? So this is 5 from this. Okay, that's the perpendicular arm, or the perpendicular distance. Okay, so we have 5 plus 120, okay, 120 sine 25 degrees plus that one, the horizontal component. But what is the but before we go further, what is the moment arm of this? Okay, so 120 sine, that's the vertical component of 120 kilonewton. That is 5. So if you're going to project this 120 sine, the moment arm will be 5. So next is plus 120 cosine 25 degrees, this one. Okay, 120 cosine 25 degrees. But what is the moment arm? Don't forget, okay, to include the moment arm, because we are having summation moments. So what is the moment arm of this 100 cosine? So if you are going to project up, and if you're going to have that, it's actually this is 3. Okay, 3 if you are going to project this. So project, then what's the perpendicular distance from here to that, perpendicular distance of this to here? So that is 3 meters. And we need to subtract RD because it is acting counterclockwise. Okay, please notice it. So from A to there, that's RD, and what's the moment arm? That is 5 and 5 plus 5, so it's 10 times 10 is equal to 0. This is actually our general equation for this particular summation moments at A. Okay, so simplifying this, so this is 500. So how about this? Plus we have 120 sine of 120 sine of 25 times 5. So that is 253.571. Then next is we have 120 cosine of 25 times 3. So this will give you 326.271 minus 10 RD is equal to 0. So collecting similar terms and transposing the unknown to the left side, so it is negative 10 RD, so we're going to put it on the left side, it will become positive. Okay, so this is 10 RD. 10 RD is equal to 500 plus 253.571 plus 326.271. So it will give you 1,079.842. Okay, then simplifying further, RD is equal to 107.984 kilonewtons. Okay, so that is for RD. Okay, so we have solved already RD. Actually, we are solving these reactions for us to have an easier way of solving or analyzing the translator. Because if you're going to notice it, in here we have already a numerical value of this joint, and of course hopefully we will be able to solve also the reactions or the horizontal vertical components of this joint for us to have a numerical value later on as we go through the analysis. Okay, so next is number 2. So since we have already computed RD, which is acting vertically, so at this juncture we can solve for RAV, this one, RAV, using the summation forces vertical, or which is one of the equilibrium equations. So another one is the next step is you need to of course have summation forces vertical is equal to 0, positive, going up. Okay, so considering all the forces acting vertically, so we can say that RAV plus RD minus 120 sine of 25 degrees is equal to 0. So we can now simplify it by having RAV is equal to 120 sine 25 degrees minus RD. So actually we have already computed the value of RAD, so we just simply do substitute. So RAV is equal to, what's the numerical value, what's the value of this, 120 sine 25, this is 50.71. Minus RD, which is 107.984. So RAV will be minus this is 50.714 minus 107.984 will give you negative 57.27 kilonewtons, or we can say that RAV is equal to 57.27 kilonewtons going downwards because of the negative sign that we had for in the final answer. So the okay, so actually let's go back again to the solution. So we have a slight mistake in there. Okay, so any observation? So let's try to go again to the solution. So we have in here, we need to incorporate actually what do you actually have in this solution. Okay, so what do you observe? So in here we had a mistake on, of course, on the summation forces vertical. We still have a 100 kilonewton going downwards, so we need to include this. Okay, so let's try to continue the solution. Let's try to correct our equation, okay, at this particular juncture. So summation forces vertical, we have RAV going up positive plus RD minus 120 sine of 25 degrees, and of course the load that we haven't included, or we have mislooked. Okay, this one minus 100 because it's going down. So let's correct it before we go further. So we have RAV, when going to the left, this will become positive 100, and this 120 sign, and RD will be negative. Okay, so substituting the numerical value, simplifying it further, so we have sine plus 100 is 150, then we have the value of RD, which we have computed earlier, 107.984. so the resulting value for RAV, or the reaction at A, the vertical component of the reaction at A, which is 42.3. So the next solution, or the next step that we're going to consider now is, of course, summation forces horizontal is, of course, positive going to the right. So as you will observe, we have used summation moments, summation moments at certain points, summation forces vertical, and of course summation force horizontal. So that's the only the equations that you're going to use in analyzing this actually. So going back to our solution, we consider summation forces vertical. So what are the forces acting horizontal? I mean, what are the forces acting horizontally? So 120 cosine, it's going to the right. Then RAH, the horizontal component of the reaction at this joint. So we just simply to have of course what is going to the right is 120 cosine of 25 degrees minus RAH. Well, this is the general equation, is equal to 0. So going again further, simplifying this, so we have RAH is equal to 120 cosine of 25 degrees. So RAH will be what? So we have 120 cosine of 25, so that is 108.757 kilonewtons. So we have already completed, or we have already computed the reactions at those joints. So at this one we have RAH, again the horizontal component of RA, and we have also the vertical component of RA. So those are the important, of course, data that we need in here for you to be able to analyze the stress of member AB and member AC. So next step is we are going, of course, to isolate joint A. So in isolating joint A, what is the most important thing that you should put in mind is the use of the, of course, the rectangular coordinate system, or the Cartesian coordinate system, the x and y, for you to draw or to illustrate the free body diagram of joint A. So we have the free body diagram at this is joint A. So we all have to redraw. RAH is going to the right, so we just simply to extend, even though this is the, so that you will not be confused. So as we all know, we have RH going, that RAH is going to the right, so that we will not be confused with the member later on. So even this one, since you have RAV, so we have RAV going up. RAV, what's the value of this? So let's try to put the values so that you will be later on be confused. RAV is 42.73 kilonewtons. How about RAH? We have 108.757 kilonewtons. No need for you, of course, to put RA in the free body diagram, because it is already represented by RAH and RAV. As I've said earlier, we just simply to need this vertical and the horizontal forces, or say components of RA. Okay, so but before that, we need to complete, of course, the free body diagram. And what will be included in the free body diagram will be this. member AB. So how are you going to have that? So you just simply draw, and uh, you need to, of course, say assume that this is in compression. So if this particular member is in compression, it will be indicated by an arrow going to the joint. So you transpose in here in the free body diagram the arrow, and you have to label it AB. Okay, for this member AB. And for member AC, so what do you think is the what do you think is the effect on the joint? Is it compression or tension? Yun lang naman, that's the only two things that you need to consider if you're going to analyze members. Are they in compression or are they in tension? Just like what we have done at member AB. So we have actually assumed that this will be in compression. So if this is addition in compression, at the other side later on, if you are going to analyze joint B, that should also be compression going to the joint. Okay, so now for member AC, assumption actually is needed. So if your assumption later on will be wrong, or it will give a negative answer, then you can change the direction. Actually, the arrowhead will just simply indicate direction. Okay, or is it in tension or is it in compression? So for member AC, I think since this is the horizontal component of the resultant RA is going to the right, okay, so it's okay, going to the left, then we can assume that member AC will be going to the left. It's just an assumption anyway. It's going to the left, right, so it is in tension na siya. Okay, so this is assumption lang naman, so we can change the arrowhead later on if it will be going to the left or it will still be going to the right. So you designate this AC or this particular arrow to be member AC. Okay, so member AC. So but what will be the slope of this? So going back to this original figure, so we have this is 3, this is 4. So what will be the 16 plus 9? 16 3 5. I'm sorry, this is 5. This is 5. Okay, I stand to be corrected. Okay, that's 5. So this is 5, this is 3. So 25 plus 9 square root of 34. So the slope is square root of 34. Okay, so this one. So we are now ready to continue the solution. So we consider this joint A. Okay, so what are unknown in this particular, or what is unknown? Actually, joint member AC is unknown and member AB. So for us to be able to come up with the correct answer, again, we need to consider, of course, what are we going to use? Is it summation forces horizontal or summation forces vertical? If you are going to use summation forces vertical, there will be two equations. I think two equations to unknown, or just simply have summation forces horizontal is equal to 0 positive to the right, because we are going to investigate. Okay, so again, so if you're going to have summation forces vertical, isa lang yung unknown, unlike I'm stand corrected as what I have told earlier. So we need to change this summation forces vertical. So this one is also summation forces vertical will be, of course, I picked up the so that this will be corrected. So summation forces vertical going up is, of course, positive. So if you use this equation, so we just simply to consider the vertical forces, the vertical component of this AB, and the vertical force that is going up. So we have 42.73 minus AB times using, of course, your slope. Okay, this is the rise and the run. So if you're going to use the vertical component of this, so we use 3 over square root of 34 is equal to 0. So AB now three over square root of 34 is equal to 42.73. So simplifying further, AB will be, so we have square root of 34 times 42.73 divided by 3. Okay, so it will give you 83.052 kilonewton. So it's positive, so most probably the direction, the arrowhead that you have indicated or you have assumed is correct. So this is in compression. We just simply to write C if it is in compression, and if it is in tension, it's capital T. So next is from this steel basing from joint A. So we have the next step is, of course, summation forces horizontal is equal to 0 positive to the right. So what are the forces acting horizontally at this joint? So you have AC 108.575, and of course the horizontal, or the horizontal component of AB. Okay, so let's try to write. So we have going to the right is AC. Okay, so we have AC minus 108.757 minus AD cosine, or we use the slope form. Okay, so we use 5 cosine, so you use 5, this one, over square root of 34. Okay, so is equal to 0. So AC now will be equal to 108.757 plus 83.052 times 5 over square root of 34. Okay, so AC will be 108.757 plus 150. So let me try to simplify first this. Okay, this one, so 83.052 times 5 divided by square root of 34. So that's 71.217. So 71.217 plus 108.757 will give you 179.974 kilonewtons. Okay, and it gave you a positive answer, so the assumption for AC going to the right is correct. So this is now in tension. Okay, so going back to our lesson, or let's try to continue it, so we have AC is in tension, so we go back to the free body diagram of joint A. Okay, so this is joint A, so we have already a value for AC, which is 179.974 kilonewtons, and for AB we have previously computed this one, so AB is 83.052 kilonewtons. So if ever we are going to again isolate any of the joints, okay, if you are going to isolate, say next is B, so whatever the value of this AC at this joint will be carried over in there. Okay, and yes, because that's the only, I think, member that is included in B, kasi yung AC is not included in here, even though we have already computed the value of AC. So if you're going to isolate, next is we are going to isolate. This is already step 5. So isolate joint B. Okay, so if you are going to isolate joint B, this one, we'll try to draw or include all the members that are involved in here. So we have members A, B, B, C, and B, D. Okay, so again, you need to have the most important thing. You should draw the rectangular coordinate system or your Cartesian coordinate system. So your y and x. Okay, so that you have a guide. So just like in here, this is your y, this is your x. Okay, so we try to draw. Okay, so we have the force 120 kilonewtons. Then we have BC. So let's try to have BC. So let's assume that this is in tension. BC is in tension, this one. Okay, this one, BC. This is just an assumption anyway. BC from here. So let's try to put BC is in tension. So tension, palayo. Kung palayo siya dito, if this is going away from that particular joint, yung effect naman dito is going away from joint C. But if ever later on, as we go through the computation and it will give us a negative answer, then we just simply change the direction. Okay, so next is we have AC. AC is in tension. AB I mean AB is in compression. Ito pala, sorry, it's in compression. This is going, approaching the joint in here and approaching in there. So AB, ito siya, this is in compression. So let's try to put the value of AB so that we have a guide. AB is 83.052 kilonewtons, and the slope will still be 3.5 square root of 34. This will not change as we go through, okay, because that's the given slope angle. Okay, so next is we have BD. So we have in here member BD. So BD has the same slope with, but let's try to assume that that is in compression. This is BD. Okay, so we have BC, BD, AC. We have a value for it, and we have this. So considering joint B, this is joint B. So we have 120. We have in here AB, which has a numerical value of 83.52, and we have BC acting vertically, and we have BC acting diagonally with a slope of 3 5 square root of 34. So this is 5. Okay, 5. This is 3, this is 5, this is square root of 34. Okay, so we now have a complete FBD, free body diagram of joint B. So let's try to start or begin with the analysis of this joint, or let's try to have it by method of joints. So we have this. First is this is solution number 5, and we have the first step. So what will be easier to compute? So we have this is BD, sorry, BD, this is BC. Okay, so if you are going to take summation forces horizontal, so we have only one unknown. Okay, summation forces horizontal, so BD is going to the left. We're going to consider the horizontal component of this is negative, so positive yung 120, the horizontal component of this, and this one is positive, is going to the right. So let's try first to write 120 summation. We'll try to write summation forces horizontal is equal to 0, positive going to the right. So what are the positive forces going to the right? 120. This, what's the angle of this? Actually we need to have the angle. This is 25 degrees, so 120 cosine of 25 degrees, because that's the horizontal component of 120, minus plus, okay, plus 83.052. then we need the horizontal component, 5 over square root of 34. Okay, minus BD going to the left times BD, what's the horizontal component of BD? That is 5 over square root of 34 is equal to 0. So if you will observe this one, this equation, we did not include the any moment arm, because it's just simply summation forces horizontal. It's not summation moments at a certain particular point. Okay, so simplifying further, we need to transpose BD. So 5 over square root of 34 BD, okay, is equal to what's the numerical value of this? So we have 120 cosine of 25, that will give you 108.757 plus 83.052 times 5 divided by square root of 34, that will give you 71.217. okay, so BD now will be what? 108.757 plus 71.217. Okay, times square root of 34 divided by 5. That's BD is 209.884 kilonewtons, and it gave us a positive answer. So our assumptions for BD, for our assumption for BD is compression, so it's going approaching the joint, so it's tension, compression I mean, sorry. So next step is we need to have summation forces vertical is equal to 0 positive going up. So we have a value for VD, so that you have a guide, and just simply to indicate in the free body diagram 209.884 kilonewtons. So doing summation forces vertical, so BC is going down, BC, force BC, and the vertical component of 120 is going down, so negative. So what are positive ones? So the vertical component of 83.0. So let's try to write. So 83.052 times 3 over square root of 34, that's the vertical component of this, plus 209.884, what's the vertical component of 209.884, times 3 over square root of 34. Okay, so next is going up, going down is 120, so negative minus 120 sine of 25 degrees minus BC is equal to 0. So that's it. So that's the equation using summation forces vertical from this joint, breakdown from this joint. Okay, so let's try to simplify. What's the numerical value of this? So we have 83.052 times 3 divided by square root of 34. So this is 42.73 plus this one, 209.884 times 3 divided by square root of 34. It will give us 107.984 for this, and minus this one. Okay, so minus 120 sine 25 degrees, it will give you 50.714 is equal to BC. So BC now will be, simplifying further, we have 42.730 plus 107.984 minus 50.714 will give you 100. BC is 100 kilonewton and it is in tension. Okay, as you can see, it is going away from the joint, so BC is in tension. We just simply write capital T, which means tension. Okay, so next step now, since we have computed BC and BD, let's try to isolate joint C. Okay, so for us to be consistent, so actually it's not necessary that you're going to isolate joints coherently. I mean A, B, C, D, etc. But if ever necessary, but it is not always done that way. So let's try to have it. Number 6 is isolate joint C. So referring joint C, this is joint C. So we have already computed BC, AC, and CD is the unknown. Okay, so let's just simply to draw again the Cartesian coordinate, or the x and y. This is your y, this is your x. So what are the forces included at joint C? So we have BC, so the same, it's going away. This is BC, which has a value of 100. Then the force that is going 100 kilonewtons, and we have also AC. Where is AC now? AC is in tension, so we are going to have this AC, so it is in tension. So we have AC, this one, so we reflect it in here, AC. But what is the value of AC? AC is equal to 179.974 kilonewtons. And last but not the least is CD. Most probably, since of course AC is this particular joint, I mean there is a horizontal force going to the left, so to counteract this, CD should be going to the right. Okay, so that's our assumption. So solving this further, analyzing this further, so first step under sixth solution, we have summation forces horizontal is equal to 0, positive going. Okay, so this is actually designated as CD. So 179.974, okay, or say let's try to have the first, or the let's try to have the positive value first. Let's try to have it, okay, so that we have similar patterns. So what's CD, which is positive, minus 179.974 is equal to 0. So CD is equal to 179.974 kilonewtons, but this is in tension because we came up with a positive answer. Okay, so anyway, we can also use joint D. Let's try to solve joint D. If it will bore or if it will give us the same answer for CD using joint D. It's just actually say counter checking. Okay, so since we have already computed all the members, why not try to use joint D for checking if it will give us CD to be 179.974 and BD to be 209 point, okay, 209.884 kilonewtons. So let's try to counter check. So we have to draw, isolate joint D. So checking, isolate joint D. So we have joint D in here. So we have RD, which is as a value of RD earlier is the value of RD. So RD is 107.984 kilonewtons, okay, and BD, okay, BD is compression. So BD, if you look in here at this, BD is in compression, so the effect at joint D will be compression also. So this is 209.884. And what else are involved at this joint? So we have CD. We have computed CD using joint C as 179.974. Okay, so we try to illustrate in here. So CD is in tension. Okay, so this is CD, which has a value of 179.974 kilonewtons. Anyway, this is just checking. Okay, so if it will bore a CD 179.974, then it is correct. So let us first remove the value. Okay, let's try first to remove the value, and let's try to have summation forces horizontal is equal to 0, positive going to the right. So we have this 209. What is 209? This is your CBD, and we have again 35 square root of 34. So summation forces horizontal, this is summation forces horizontal is, we have CD going to the left, so positive 209.884 times 5 over square root of 34 minus CD is equal to 0. Okay, then CD is equal to 209.884 times 5 over square root of 34. So simplifying further, we have CD to be, okay, so we have 209.884 times 5 divided by square root of 34. This is 179.974 kilonewton. This is tension. So did we have the same answer using joint C and joint D? So if you look at the answers, they are the same, they are equal. Okay, so we have analyzed the thrust correctly. Okay, meaning if you will use a particular joint with its data to counter check the answers at the other joint, we can do that, and if it will give us the same answer, then our process is correct. Thank you.